This is section 9.7a, probability. Any activity with unpredictable results is called an experiment. And by unpredictable, we mean that you just can't know exactly what it'll be. You might know what the different possibilities are, but you don't know exactly what it's going to be. You know, you flip a coin, might be heads, might be tails, can't be anything else, but you still don't know for sure what it'll be. So any activity with unpredictable results is called an experiment. The results of an experiment are called outcomes, and the set of all possible outcomes is the sample space. Again, what we're doing, as we often do in this course, is just introducing terms, because part of math is, learning the language and, being able to recognize the terms when you see them. And these terms are used when we discuss probability. The number of outcomes in the sample space, S, is symbolized by N parentheses S parentheses. And that N just stands for the number of outcomes in the sample space S. So let's look at some examples, and that will help us to understand these terms better. We're going to look at some experiments, their corresponding sample spaces, and the number of outcomes in the sample space. So, classic experiment, flip a coin. This is an activity with an unpredictable result. Flip a coin, you might get heads, you might get tails. That's why the sample space consists of two possible outcomes. H stands for heads, T stands for tails. And NS, the number of outcomes in the sample space, is 2. Another experiment would be to toss a die. When you have 2 die, we call them dice. But if you just have one, it's called a die. And as you know, a die has 6 faces. So to toss a die is an experiment because it has an unpredictable result. The sample space of that experiment is 1, 2, 3, 4, 5, 6. These are all the different die faces that we can get when we toss a die. And you probably already figured out that the number of possible outcomes in the sample space, or NS, is 6. Okay, any subset of the sample space is called an event. So the number of outcomes in an event, E, is NE. Now let's look at what we mean by that. Here are some examples to clarify what we mean by event. So let's, look at some experiments, events, the corresponding subset of the sample space, and NE. So let's go back to flip a coin. Flip a coin is the experiment. The event now that we're talking about is that I get heads. All right, now remember on the last screen that the sample space for this experiment, flipping a coin, the sample space was HT. An event refers to a subset of the sample space, and that's why this event is just getting heads. Getting heads is a specific event for the experiment of flipping a coin, and that getting heads is the subset of the sample space, H, and the number of outcomes in that subset is 1. Now let's look at the experiment of tossing a die. We know from the last screen that the sample space, the total sample space, consisted of 6 possibilities. But the event that I'm talking about here is a subset of the sample space to get an even number. When you toss a die, if you want to get an even number, that's an event because that's a subset of the sample space. And that subset is 2, 4, 6. These are the only even numbers within the sample space. And the number of events in that subset is 3. Okay, the number of outcomes, in that subset is 3. So we toss a die. The event is getting an even number. That's a subset of the sample space consisting of 2, 4, 6. And the number of different outcomes in that subset is 3. What about the experiment of drawing a card? drawing a card? Well, a possible event for the experiment of drawing a card is to get an 8. So what are all the different ways that we can get 8s? Well, there's the 8 of spades, the 8 of hearts, 8 of diamonds, and the 8 of clubs. This would be the subset of our sample space, which we can also call the event space. And this subset of the sample space consists of 4 outcomes, and therefore NE is 4. So hopefully you're getting the feel for this. How about flipping 2 coins? All right, flipping 2 coins, we have 2 different events, right? And we saw this in the last lesson. What happens when you have independent events? Well, let's say that we want to get at least 1 head. Well, this is the subset of the sample space. The total sample space would be HH, HT, TH, TT. HH, HT, TH, TT. But notice here that in the subset, we don't have the TT outcome, the tails, tails outcome, because that tails, tails outcome would not qualify for the event getting at least 1 head. And so the subset of the sample space then would be HH, HT, TH, because all of these 3 outcomes have at least 1 head. HH has 2 heads, but that C2 is still at least 1. HT is 1, TH is 1, but TT, the outcome PT, will not fit in this subset of the sample space. It will not fit in this event space because it does not meet the criterion of getting at least 1 head. And the number of outcomes in this event is 3. 3 possible outcomes for the event of getting at least 1 head in the experiment of flipping 2 coins. Now let's put all that together into a formula, which you probably already learned. You probably already learned it in Algebra 2. The basic formula for probability with a numerator and a denominator, it's this. The probability of an event equals the number of outcomes in the event space divided by the number of outcomes in the sample space. That's what this basic formula means. The probability of an event equals the number of outcomes in the event space, which is a subset of the sample space, divided by the number of outcomes in the sample space. Okay, let's see this formula in action. If the number of events, or the number of outcomes in an event space is 0, then the probability of that particular event is 0, and the event is impossible. So what do we mean by an impossible event? It means that it has a probability of 0. It simply cannot happen. If the number of outcomes in the event space is equal to the number of outcomes in the sample space, that is, if NE equals NS, then the probability of the event, PE, is 1, and the event is certain. Okay, so a certain event has probability of 1, an impossible event has probability of 0. What would be some examples of impossible and certain events? For example, let's say we roll a 6-sided die. The probability of getting a 10, if I just roll once, it's 0 out of 6, because there is no 10 face. And so it is impossible to roll a 10 if you roll a 6-sided die once. You cannot get a 10, right? And that's pretty obvious, right? So that's an impossible event. How about a certain event? Well, when I roll a die, a 6-sided die one time, I know with absolute certainty that I'm going to get something that's less than 10. I'm going to get some face that's less than 10. Therefore, there is a 6 out of 6 probability, or probability of 1, and it's certain. Now, most of the probabilities we're going to deal with are somewhere between impossible and certain. But this is just so that you understand what the terms mean. Let's look at this example. Say 2 coins are tossed. What is the probability that at least 1 head comes up? Okay, well, my sample space, the total sample space for this experiment is HHHT, like we talked about before. These are all the different possible outcomes that I can get for the experiment of tossing a coin, tossing two coins, or tossing a coin twice. But tossing two coins is really going to give me the same outcomes, the same possible outcomes. Okay, so that's my sample space. My event space is HHHTTH because these are all different outcomes that have at least one head. And going back to the formula of PE equals NE over NS, well then it's simply a 3/4 probability. So if I toss two coins, or if I have, toss one coin and then toss it again, if I toss two coins, the probability that at least one head comes up is 3/4. There's a 3/4 probability of that event. Another example, a card is drawn at random from a standard deck of cards. What is the probability the card is a face card? All right, to challenge yourself then and to help you learn this material, try to pause the video and do this on your own, and then resume if you get stuck or when you have an answer. So our sample space is all 52 cards in the deck, and therefore NS is 52. Okay, that part I'm sure you got. Now our event space consists of all the different possible outcomes, all the different ways that I can get a face card. Right? And this is all like, drawn out for you here. These are all the different face cards in a deck. We've got the Jack of Spades, Jack of Hearts, Jack of Diamonds, Jack of Clubs, Queen, 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 King, 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 King. All right, these are all the different face cards. And that's the event space. Well, the NE, or the number of outcomes in the event space, is 12. And therefore, the probability of drawing a face card from a 52 card deck is 12 over 52, and that is equal to 3 over 13. So there's a 3/13 probability of drawing a face card from a standard deck. Another example, two dice are tossed. What is the probability of getting a 7? Again, pause the video, try to do this on your own, and then resume when you have an answer or if you get stuck. First, we need to figure out our sample space, all the different possible outcomes of rolling two dice. We could get a 1-1, a 1-2, a 1-3, a 1-4, a 1-5, 1-6, 2-1, 2-2, 2-3. All right, you could just, write all these out if you want. That's kind of doing it the long way. But the easier and better way to figure out the sample space for this event is to realize that each roll is an independent event. And if the first roll, okay, I'm kind of highlighting that with arrow, if the first roll has 6 different outcomes and the second roll has 6 different outcomes, well, 6 times 6 is 36. And so if you were to write all these out by hand, just writing out all the possibilities, you would find that there are 36 possible outcomes. But it's certainly faster to just do 6 times 6 and get 36. Our event space, these are all the different ways that I can get a sum of 7. 1, 6, because 1 plus 6 is 7. 2, 5, because 2 plus 5 is 7. 3, 4, 4, 3, 5, 2, 6, 1. This is my event space. And my probability then of this event is the number of elements in the event space, which is 6. See, this is 1, 2, 3, 4, 5, 6, divided by the number of outcomes in the sample space, which is 36. So 6 divided by 36 is 1/6. And therefore, when I roll two dice, I have a 1/6 probability of getting a sum of 7. Another example, let's say I give you 20 study problems in a review session, from which 10 will be on a test, and you know how to solve 17 of them, what is the probability that, first, I will make a test in which all 10 problems are from the 17 study problems that you know? Well, this is kind of a risky way to prepare for a test. If you have 20 study problems, ideally you want to know all 20. But let's just say that you only knew 17. From your standpoint, what's the probability that I, as a teacher, will make a test in which all 10 problems are from the 17 study problems that you know? Now, keep in mind that as I make this test, I have no idea which are the 17 problems that you know. Okay, so this is the probability from your perspective. You go into the test blind, you have no idea which 10 I'm going to give you, but you want to find the probability that the 10 I will give you on the test are all from the 17 that you studied. Okay, I'm going to walk you through this because this is a little bit difficult, but hopefully when you see the solution, you'll kind of understand how to do this. What you have to do is you have a numerator and a denominator because this is a probability problem. And so your numerator is going to consist of your number of outcomes in the event space, and the denominator will consist of the number of outcomes in the sample space. And that looks like this, okay, 17C10 over 20C10. Let's look at why this is true. Okay, remember we did combinations in the last section. And so this is a combination of n elements taken r at a time. Okay, that's nothing new. But why 17C10? Okay, because I know that there's a pool of 17 problems that I know. And this 10 is a subset. That's my r. These are 10 that are taken from the subset of 17. Sorry, the 10 is a subset from the total set of 17. So I have all these different ways in which a test could be given, in which all 10 problems are from the 17 that I know. Okay, so the numerator is 17C10, but the denominator is 20C10, because this now, of course, is the bigger number, the denominator. The 20C10 represents all the different ways that a 10 problem test can be made from a total of 20 problems. Okay, so this is the denominator. These are all the different 10 problem tests that can be made. Whereas the numerator represents all the different 10 problem tests that can be made only from the 17 that I know. All right, and that probability is 0.1053. Which means that if you only study 17 problems out of the 20, and you do that hoping that, I'm going to make a 10 problem test only from those 17, well, you really only have a 10% probability of getting a 100% grade on the test based on this ratio. Now let's say I make a test in which at least 8 of the 10 problems are from the 17 study problems that you know. Well, this is obviously going to raise the probability. And it means that you're going to get at least a B minus, right? At least an 80%. But how do we figure out this probability? Okay, this is a little bit hard also because the first time we're doing these kinds of problems. So I'm going to walk you through the first step, and from that you should have enough information to go through the other steps. So let's pay attention to the question. What is the probability that I will make a test in which at least 8 of the 10 problems are from the 17 study problems that you know? Okay, we have to break this up into parts. And the first part, this is the hint and the first step that I'm walking you through. You know 17 problems and you don't know 3. This is important to keep in mind. There are 3 that you absolutely don't know. The probability that I will make a test in which exactly 8 of the problems will be from the 17 you know is 17C8 times 3C2 over 20C10. Okay, now, first of all, before we go into that, let's explain why we need to know the probability that exactly 8 of the problems will be from the 17 I know. Notice that this original question is asking for the probability that at least 8 of the 10. Okay, the at least is important because if 8 of the 10 problems are from the 17 that I know, or if 9 of the 10 problems are from the 17 that I know, or if 10 of the 10 problems are from the 17 that I know, those possible outcomes all fit the criterion of my knowing at least 8, right? Of the test takers knowing at least 8 of the 10 problems on the test. That means we need to break this up into parts. And so we need to have the probability of having exactly 8 that I know. Then we're going to need the probability of having exactly 9 that I know. And then we'll also have the probability of knowing exactly 10, that 10 out of the 10 problems are from the 17 that I studied. And adding those three probabilities together will give us the probability of getting a test that has at least 8 of the 10 problems coming from the 17 that I studied. Okay, now let's look specifically at this 17C8 times 3C2 numerator. Okay, so the 17 here is the pool of problems that I studied. The 8 is the subset of that pool. Okay, so this 8 represents the 8 questions taken from the 17 that I know. And these are the 8 questions that I will know on the exam. Now, the reason I multiply that by 3C2 is because I also need to take into account the 2 questions on this exam, which are from the 3 problems that I don't know. Okay, so that's why this 3 is here. Notice that this 3 plus this 17 add up to 20. So this numerator accounts for all the different 10 problems that I can get on this test. But the reason I need to multiply it by the different possibilities of questions that I don't know is because for every combination of 8 questions that I do know from the 17, there's going to be certain possibilities for the 2 that I don't know, and that's given by 3C2. 3 total ones that I don't know, and 2 from that are going to make up the 2 problems on the test that I don't know. Okay, so this whole expression, 17C8 times 3C2 divided by 20C10, gives me the probability of getting a test in which exactly 8 of the 10 problems are from the 17 that you know. Notice that the numerator here is the same because the denominator here, 20C10, this is the same. The 20C10 is the same denominator as the 20C10 up here, the one that I'm circling now with the arrow, because that doesn't change. The denominator always is the same because the denominator always represents the total number of ways that a 10-problem test can be made from a total of 20 possible problems. Okay, so now let's go back to the original question. What is the probability that I will make a test in which at least 8 of the 10 problems are from the 17 study problems that you know? Recall that this is only the first step, the one that I walked you through, because this only tells you the probability of getting exactly 8. What we need to do now is take into account the other probabilities of getting exactly 9 and of getting exactly 10, which, added together, will give me the probability of at least 8. So pause the video, try to do that on your own, and then resume when you have an answer. Alright, this is what it looks like, the total solution. So this is the part that I walked you through. This is the probability that I will make a test in which you know exactly 8 problems. 17C8 times 3C2 divided by 20C10. 17C8 represents the 8 problems on the test that you do know. The 3C2 represents the 2 problems on the test that you don't know. And the 20C10 represents all the different ways to make the 10-problem test out of 20 possible problems. Now, what are the 2 steps that were missing in the last screen that you needed to fill in? You also have to add the probability of that I will make a test in which you know exactly 9 problems, and you need to add that to probability that I will make a test in which you know exactly 10 problems. Notice that all these probabilities together, when we add them, gives us the probability of getting a test in which you know at least 8. Why? Because a test in which you know exactly 8 is at least 8. A test in which you know exactly 9 is also at least 8. And a test in which you know exactly 10 is also at least 8. That's why we need to add all these together. And when we do the math and calculate all of this, we find that the probability is 89%, which is significantly higher. There's a probability that at least 8 of the 10 problems on the test will be from the 17 that you do know. Here's the classwork, page 709. Please copy these numbers down, and we'll see you in class.